Hello and welcome to this training film covering the process and procedures for insulation testing of high voltage cabling and components on an electric vehicle. Before we look in more detail at the specific methods to be applied when carrying out high voltage insulation tests, it would be a good idea to recap how to use an insulation tester, but more importantly, to understand how and what it is actually measuring. We should all by now be aware that electric vehicle high voltage drive lines use a double insulated Class 2 wiring architecture. Put simply, double insulated means the electrical supply consists of only a positive and negative circuit. There is no earth as used by mains Class 1 electrical supplies. These two circuits are then insulated and shielded away from each other or shielded away from every part of the vehicle. The high voltage circuits are encapsulated in a main insulating layer or sheath, and then a layer of supplementary insulation which, for high voltage vehicles, is actually a metal shield or screen, similar to the screening around a coaxial cable, but a much thicker gauge. The function of an insulation test then is to check that these two high voltage circuits are still insulated and shielded and not coming into electrical contact with any other part of the vehicle. To put it another way, the high voltage is not leaking out through the insulation into the rest of the vehicle. The next obvious question is, how can a metal shield or screen around the high voltage circuit be classified as insulation? Surely it should be non-conductive. The answer is that the supplementary insulation has more than one function. The screen is connected to the body earth of the vehicle by equipotential bonding straps. All the high voltage cables and components are shielded within this metal screen, which constricts the strong electromagnetic fields emitted by the high voltage currents. Otherwise, these magnetic fields would interfere with the operation of the electronic control systems in the vehicle. In some areas, the screen also acts as a physical shield against accidental cable penetration or damage. As an insulating screen, it works as a main insulation failure detection system. The first point of contact for the high voltage, should the main insulation fail, will be this earth screen. The vehicle systems can constantly monitor this to check the insulation is intact. Any insulation failure detected via the insulation screen, and the vehicle control systems disconnect the traction battery high voltage supply. This also makes the screen a reference test point when carrying out a manual insulation test using the insulation tester. Again, checking the screen is not electrically contacting in any way with the vehicle's high voltage circuits. To get a better understanding of how an insulation tester works, we need to do a bit of electrical theory. So here goes. An insulation tester works in exactly the same way as a normal multimeter, set for resistance testing and then being used to check for an unwanted mutual short between two electrical circuits or cables. In the case of an electric vehicle insulation test, the two circuits we are checking for a short are between the positive high voltage circuit and its insulating screen or shielding, and the negative high voltage circuit and its insulated screen or shielding. Multimeters are fine for checking mutual shorts on 12-volt circuits, but when we're dealing with 400 volts, for example, a multimeter would only pick up a short circuit which are perfect with little or no electrical resistance at the point of contact, creating the short. This is due to the very low voltage they push out to do the test, usually around 1 volt. They do not have the voltage pressure to check if high voltage would push through the resistance at the contact point of a short. Remember, a short circuit resulting from damage to an electrical circuit or the breakdown of insulation rarely creates a perfect short. There's usually some electrical resistance within the point of contact, creating the short circuit. However, when we're dealing with high voltages, the high voltage has the electrical pressure to easily push through quite high resistances, creating short circuit to the supplementary insulating shielding or screening. Therefore, we have to check our main insulation's integrity or performance using a voltage preferably higher than the maximum voltage the vehicle's circuits operate at to see what leakage, if any, we have. Our current EV drivelines can operate at a maximum possible voltage of 450 volts. Therefore, the insulation test is undertaken using a test voltage of 500 volts. The measured resistance value indicates the condition of the insulation between the high voltage circuit and the supplementary screen. An infinite resistance or open circuit will be the perfect result, but no insulation is perfect, especially inside electrical components. So the higher the reading, the better. If you like, the megaohm resistance value indicates how good the insulation actually is. Hopefully now it's clearer how we are using the insulation tester to check and test the condition of the main insulation around the high voltage cables and components. We need only apply the same procedures as we would using a standard multimeter to check for a mutual short, but the readings we get are not quite what we'd normally expect. The difference is the value read on the insulation tester is given in megaohms, because we're measuring the level of insulation around the circuit tested, and the reading we see is often far from stable. It's fluctuating with values rolling up and down. To understand this more, we need to look at the difference in how an insulation tester is measuring the resistance compared to a standard multimeter. You will notice that on activation of the insulation test, the tester bleeps, in sequence with a flashing red LED. Each bleep and flash represents a pulse of electricity which builds up the voltage over a few seconds from 50 or 100 volts up to the selected test maximum, for our purposes 500 volts. It's not a constant output. In addition, any capacitance in the component or circuit being tested also generates an increasing opposing voltage. Furthermore, the tests we are instructed to carry out are in many cases an imperfect resistance test. Remember, correct test procedure requires the complete isolation of the circuit to be tested and no other voltage to be present. High capacitance in components, as we mentioned earlier, creates an opposing voltage, and we may not be properly able to isolate the circuit we are testing. Not ideal conditions then. But rather than have to disconnect everything in the vehicle or the components you are testing, PSA engineers have pre-tested good circuits to take into account these less than ideal test conditions. All these variables together can produce the fluctuating value you're trying to read on the tester. This is also why the recommended test duration is always more than 10 seconds, with a 1-minute test recommended for larger circuits to put the insulation under pressure and to properly assess the minimum megaohm reading being shown. For electric vehicle insulation test purposes, PSA will give a resistance value for the specific circuit or component to be tested. This resistance value is a threshold value or reading, below which any actual test results must not drop. For example, not less than 2 megaohms. The insulation test resistance threshold values PSA provides are normally in the megaohms when testing high voltage component insulation or the insulation integrity of the complete high voltage driveline. Occasionally the meter may fluctuate up to a reading of just 1. This represents an infinite resistance, referred to in the documentation as OL, out of limits, or occasionally even as a high gigaohm reading. In plain English, this means perfect open circuit. Always double check your probe connection points if this happens to ensure you have a good reading. Disconnected high voltage cables tested separately should always give an open circuit reading, or just one, as the screen and the conductors should be perfectly insulated from each other. As long as the value read is equal to or greater than the resistance value published by PSA for the test, the main installation is serviceable and safe. Now we've done the theory, let's put it into practice. We understand exactly how we're testing the installation and what results to expect. Let's work through some examples to see the testing method in action. Before every use of the installation tester, we must remember to check the tester itself to ensure it is safe to use and performing correctly. To do this, we follow the manufacturer's instructions. First, we carry out the 3 checks on the test leads themselves. First, check to ensure they have Cat 3 600 volt or higher installation rating. Second, we check them for any damage to the installation connections or terminals. And third and final check is a continuity and resistance test. We need a very low internal resistance of no more than 0.6 of an ohm really. This is easily done by using the normal resistance test settings, coloured orange, on the installation tester. Next, we need to check the test voltage output of the installation tester to ensure the output is 500 volts or more. For this, we use an additional multimeter, which also enables us to check the installation tester is reading correctly. Standard multimeters have an internal resistance for voltage testing of approximately 10 to 11 megaohms. So, with the test leads connected to our multimeter, we not only check the output is 500 volts or above, but looking at the installation tester display, we should be able to read the multimeter internal resistance of between 10 to 11 megaohms. Remember, the same test and checks must be applied after completing any measurement testing to ensure the installation tester was emitting 500 volts throughout the duration of the test. Where there's no specific recommendation on test duration, we recommend using 1 minute, though for some tests on single circuits or components, the instructions will state for at least 10 seconds. You must not test for anything less than the time given. Always go over if not sure. The first installation test we will use as an example is the one we should all be familiar with, the complete electric vehicle high voltage driveline circuit test, which must be completed on every electric vehicle as part of the power-up procedure. For this, we will use one of our current BEVs. The vehicle is already powered down and made safe, and we've already checked the installation tester's functions. Following the instructions in service box, it tells us to put the negative probe on the earth at E of the electrical power circuit connector. This is the earth shield or screen which is wrapped around the insulated high voltage supply wires. Put the positive probe on the pin at D of the electrical power circuit connector, and this is one of the main high voltage supply pins. Check the resistance value is higher than 2 megaohms. As we run the test, we can see the resistance reading starts at around 6 to 7 megaohms and climbs up and fluctuates at around 10 megaohms, but it's always going up and is well above the minimum threshold reading given in service box of 2 megaohms. We then repeat the process for the other pin on the connector, testing the resistance value between the high voltage central pin and the opposite earth screen. Put the negative probe on the earth at E of the electrical power circuit connector. Put the positive probe on the pin at F of the electrical power circuit connector and check that the resistance value is higher than the threshold 2 megaohms stated. In the film clip, you may have spotted that the test was done using the opposite probes to those given in the instructions. However, when carrying out any resistance testing, the polarity of the test probes has no effect on a resistance test. Both tests gave resistance values well above the 2 megaohms threshold value given, meaning the insulation is intact and not damaged. Now let's have a look at testing the resistance of just one main high voltage component. For this, we're going to use a PTC heater fitted to a PHEV as an example. It is important to read the test instructions carefully and to ensure you're using the contact points for the test probes exactly as described in the instructions. Pay particular attention to exactly how you're being asked to carry out the test. Is it referencing the earth screen or shield point in the connector? Or is it using a separate earth point on the vehicle? A separate earth is normally used when access to the screen or shield is not possible within the connector itself. Ensure you're contacting the test points as shown or described in the instructions, as the wrong test point will give you a different resistance value, which could lead to the wrong diagnostic result. There are a few words of caution before we start. Please remember to power down the vehicle first, as instructed, before starting any work. And when probing connections, be careful. Ensure you can clearly see the pin you are contacting onto. Do not apply too much pressure. Even though these are high voltage connections, it is easy to bend or damage some of the pins by being heavy-handed. If a connector will not clip back in place easily, check the pin alignment. Do not force it. Having completed the powering down procedure for a PHEV, we're now ready to carry out a test on the PTC heater as instructed. These test instructions are in the form of a flowchart. After powering down the vehicle driveline, the installation test for the PTC heater starts at the already disconnected high voltage supply cable at the traction battery. Using the PTC heater connection, it asks for the following checks to be carried out and the results to be recorded. High voltage plus to shielding measurement, followed by high voltage minus to shielding measurement. After recording the results, following the flowchart down to the either or results box, which states if R is greater than 100 megaohms, result yes. Move on to check the next component. Result no. Disconnect the high voltage cable connection at the PTC heater itself. However, this was a good result with a reading which scrolled up to infinity or 1. But let's assume we had a reading of less than 100 megaohms. Back to the flowchart, which instructs us to disconnect the PTC heater and test this separately. For filming, we've removed one from underneath the vehicle so we can clearly see the test. The flowchart instructions ask for a check between high voltage plus to PTC earth and high voltage negative to PTC earth. The either or result box on the flowchart states if R is greater than 20 megaohms, continue on to check the high voltage supply cable. If no, remove and replace the PTC heater. The result, as we can see, shows a resistance value well below the 20 megaohms threshold, so this heater is the cause of the installation failure and must be replaced. If the PTC's heater installation on test proves to be good, the instructions say check the installation on the high voltage cable. By a logical diagnostic process then, this will show a short of the installation. Remember, a high voltage cable should always give a perfect open circuit reading showing as 1 or infinity on the meter. Well, thank you for watching, and we hope this training film has been helpful. Remember, you can always recap any part of this film or the previous theory section by accessing the links shown on the screen.